Yeah, as Hamish said, the thermodynamics approach is really it's a behavioral approach that you have the components each having following certain rules, and they're hooked up together, just as before, just the normal ThermoFlo approach. The first thing I want to show is refrigeration systems. Here we're talking about vapor compression refrigeration cycle. Things that are normally we're looking for is the heat removal from the refrigerator space, power requirement, efficiency, and that sort of stuff. So we look at a simple video next that actually shows how you can put together this example. Let's say we want to solve a two-stage refrigeration system that you have a high pressure and low pressure compressors, and we have a condenser, and then you get the valve that gets the pressure down to a flash chamber, and the flash chamber you get part of it, you get the extract the steam out, and then you get the liquid go down to the evaporator, and then you have a low pressure compressor. And in this problem, we know the pressure level, then we're trying to figure out what's the evaporated mass fraction and the usual things. With ThermoFlo, you basically drag and drop things on the screen regardless of the complexity of your problem, and it will give you all the information you're requesting. So here first we create a model, we give it a name, two-stage refrigeration, I guess. And with that, it opens up your screen, and we see the main canvas. I just make it a little bit bigger so we can use your components. So we go to the thermodynamic components. We get a high-pressure compressor up there. So we have the high-pressure refrigerant going into a condenser, and then from the condenser we need a valve, and the valve gets the pressure down to a flash chamber pressure, which is our intermediate pressure. So we put it right there. And then we need another valve to get the pressure down to the evaporator pressure. Now we need the evaporator, and we get the evaporator, and you just put it wherever you want on the screen. And then we need a mixing chamber to get the fraction of the flows coming from both sides before it goes to the high-pressure compressor. So we need a low-pressure compressor down there that's attached to the evaporator. Now you can just put things, make it look nice and all that good stuff. After that, all you need to do is just get the outlet of one component to the inlet of the next, and that's how you put your system together. You need to keep in mind that when you connect things this way, these are ideal connections. There's no pressure losses in these things. If you wanted to look at the pressure losses, you could put a pipe system there. So now we just connect things together this way, and everything is connected. So just make it look a little bit better. So now the next thing we want to do is to go and set the loop fluid. So we go there and we choose the fluid. By default, you get water. Here we need a refrigerant. So we double-click on it. You have all the NIST materials available. So here we go to the refrigerants, and we want to pick 134A. And we pick that. So that's now our fluid. Now here's a good place to give the mass flow rate, because that's where all the flow merges. So we get a mass flow rate at that point, double-click on it, and we give it 1 so we can do per kilogram analysis. And now let's set the pressure levels. So we go to the inlet of the low-pressure compressor. We set the pressure there at 0.14 megapascal. Just get the pressure thing and enter 0.14. Change the unit to megapascal. The same as said, you could just change your defaults to what you want, so you don't have to change it every time. So here's our low pressure, and then we go set the highest pressure in the model at the outlet of the high pressure compressor, and I believe that's 0.8 megapascal. We set that right over there. And again, we want to make things look nice. You can just put it out of the way and and do all the line up the lines. And then we go and set the pressure at the intermediate pressure when it's coming out of the first valve. So we just set the pressure there at 0.32 megapascal. Okay, and we're almost done. Now we need to just set, if this is an ideal system, What comes out of the condenser is going to be a saturated liquid. So at that point, we just go there and set quality equal to 0, which is the default value. So I don't have to do anything with that. Just clean up a little bit. And also at the bottom, we have an evaporator. If it's ideal, it's going to come out as a saturated vapor. So we go there and we set that quality equal to 1. That's about all you need to do. You can solve the problem. No need to look up steam tables, refrigerant tables, and iterations and all that. Now let's look at, if you wanted to see the compressor, you double click on it, you take you to the menus. Whatever's not checked will be calculated. So, and then you go on, let's look at the evaporator, for example. You can look at the things, if you wanted to use here, we chose to give the pressure drop of 0. That's the ideal thing. If you didn't want to, you could just take the effect of all the things in it. So now you run it, click a button, and it's done. And the results come by default. Temperature is shown as all the nodes. I'm going to turn that off. And if you right-click on any component, you can see the abbreviated results of summary results of this component.